Hello everyone, I'm Vikram, a computer science master student at Columbia University.
And I'm Sarthika Dhawan, a software engineer at Microsoft. Today, we will be talking about parallel and distributed programming in Python using a standard called Message Passing Interface or MPI. So, we will be using MPI from going onwards for message passing interfaces. Now, let's talk about the agenda. We will start with a quick discussion on the key differences between concurrent and parallel programming, followed by detailed discussion on the crux of our presentation, that is MPI, and how to use it in Python. We will also discuss MPI for both parallel and distributed programming along with some examples. And then a quick glance on things to consider while writing parallel code and what mistakes to avoid will give us an overview of the best practices to follow. So in this talk, we will skip past some theory and focus more on the practical aspects. This talk can serve as a starting point for someone venturing into MPI, using MPI for the first time. And finally, we will conclude the talk with a fun trivia and a Q&A session. Now, let's first discuss the two main ways in which performance of programs can be improved. The first way is loosely called content programming, and the second way is called parallel programming. Now, concurrency is an umbrella term, but for this talk, we use it to mean something specific. So let's consider these two figures at the top. In both of these, there are two tasks, T1 and T2, that need to be executed. And each task is divided into multiple pieces. In the left one, T1 and T2 are interleaved, as you can see, but at any given instance, only one among T1 and T2 is getting executed. But in the second one, there are times when both T1 and T2 get executed at the same time. So we call the left one style left is as the concurrent one, and the right as the parallel one. Strictly speaking, we exploit the general term concurrent to mean the left side. Of course, the right scenario is not possible always, but for most of the modern machines and a lot of problems, it is. The heading of the slide, basically interruptibility and independability. These are not actual English words, but they do a good job in making us understand the key way in which concurrency and parallelism differs. Now we will discuss concurrent programming in a bit more detail. So as explained previously, concurrency is execution of multiple instructions within same time frame. So one way to achieve this is through time slicing, where the computer switches rapidly between different tasks. Given the appearance of simultaneous, it gives the appearance of simultaneous execution, but it is not exactly happening in parallel. So you can take an example of a queue in a bank. So if there are two queues in a bank, if there is a separate queue for senior citizens, and there is only one teller, so the teller will alternatively switch between the two queues, thus making both the queues progress. But they progress in a sharing manner. Like at a time, only one queue, a person from one queue is only uh, progressing. So concurrency is a semantic property of a program, meaning it depends on the design of the problem at hand, and the task should be such that it can handle switching. So this is different from parallelism, which is an implementation property, as we will discuss later. And concurrency increases the responsiveness of the system as it allows multiple processes to share the resources. The usual ways in which concurrency is achieved is using threads or processes or asynchronous programming. But we will not delve deeper into these topics. We will focus more on parallel and distributed programming. This was concurrency, but like if you run a CPU intensive operation in a thread, it will be paused when the runtime switches to another thread. So there will be actually no performance benefit over running the operation outside of a thread. So what can we do to achieve more? So like in Python, and there is a global interpreter lock, in which Python interpreter design allows only one Python instruction to execute at a time. Now this is a limitation of global interpreter lock, but it can be completely avoided by using processor instead of thread, and we will see how. So parallel programming. Now, like let's discuss about parallel programming. As evident from the previous discussion, parallelism is the actual physical execution of multiple instructions at the same time. And if we take the same example as the queue at the bank, which we discussed earlier, now imagine there are two like counters. There are like two tellers sitting at the bank, and there are and same two queues are there. So now, since each teller can execute like process each queue separately, so both the queues progress parallelly, and they don't have to wait on each other. So it's not they're not time switching; they're actually executing in parallel. So that is the analogy. Now, Parallelism is execution of multiple instructions at the same time, as we discussed, and it's about maximizing the hardware resources. So, like if you have eight CPU cores or four CPU cores, you don't want to use only one, and while others sit idle. So you want to maximize all those resources and take the full advantage. So apart from designing code, it also involves changes at hardware level because it requires multiple computing sources and syncing between them. So yeah, so this is about parallel programming, and it can be achieved using multiple cores in a single processor or even between different machines. So the former is parallel programming, and the latter one is the distributed programming, which we will discuss later. And parallel programming can be achieved using MPI, OpenMP, or pthreads, and several other paradigms are there. But in this talk, we will be discussing about MPI in detail. Yeah. So now comes MPI. So it's a language agnostic model communication protocol for writing message passing programs. Now, what is message passing? So message passing provides a mechanism to allow processes to communicate and to synchronize their actions without sharing the same interspace. So in this approach, what happens is processes send messages to each other to exchange information, and then they coordinate their work, and then they finally communicate the results. So it's a standardized and portable library. MPI is actually a standardized and portable library specification for message passing and parallel computing. And it provides all those sets of functions and routines that will allow the processes to communicate with each other and finally conclude a result. And MPI is a SPMD. So SPMD is basically single program, multiple data. It stands for single program, multiple data. So there's a same program, but it is run on multiple processes, and every instance of the program knows which part of the computation it should perform, and the results of the computation are combined later. So in summary, message passing is a general concept, and MPI is a specific implementation of message passing for parallel computing. Now, this all sounds great, but then why don't we use MPI everywhere? So there is a drawback. It's challenging to develop programs using MPI, but in this talk, we will give a head start on how to actually develop programs using MPI, and we will see how they are actually doing the computation.
Yeah, so before proceeding further, we would like to discuss some basic terminologies that will be used in the future slides. So first is distributed memory and shared memory. So as you might have guessed by the name, distributed memory is having a separate address space and shared memory is having a common address space. Next is process. So process is an instance of a program running on a computer. So in MPI, multiple processes can run on separate nodes or computers in a cluster, and then they work together to solve a problem in parallel. Then there is communicator. So communicator is a group of processes that can communicate with each other in MPI. And it defines a context for communication, including the number of processes and the ranks of each process. So rank is basically a unique identifier for within a given MPI communicator, and each process is assigned a unique each process is assigned a unique rank. So it's used for identifying the processes in the communicator. And then there is size. Size is basically the total number of processes within the communicator. So it actually defines the range of the rank. So the rank ranges from 0 to size minus 1. Then there is a default communicator provided by MPI, which is called MPI Com World, and it so it's possible to create custom communicators in MPI, but for this talk we will be using the default one, and a single process can belong to multiple communicators and have a different rank in each one. So it's not mandatory to have a process belong to a single communicator. It can be distributed in different communicators. Now I would like to hand it over to Vikram to discuss MPI for Python in detail.
Yeah, so now that we know what MPI is, to summarize quickly, MPI is a way in which you can run a particular program on multiple computing resources, be it cores, different cores in your CPU, or be it actually different machines. So if I have a group of 5 computers, I can use MPI so that my Python script can run simultaneously on all those 5 computers. So MPI gives us a way for doing that. Now, as we already know, MPI is not a language, is not a framework, it's just a standard. So how do we use MPI in Python? So there's a module called MPI for Py, which is provided in Python, which provides bindings for this framework, not a framework, this standard in Python. It uses pickle-based communication for generic Python objects. Now, as you might know, pickle is a kind of a format in which Python objects are stored, and MPI leverages this format to communicate for the processes to communicate with each other. Like MPI literally means message passing interface. So there should be a way in which these messages are passed. And so that's how it uses pickle. And moreover, the speed of communication is really fast. In some buffer provided objects like NumPy arrays, for example, it is as fast as the programming language C, which we know is really fast. Now, how do I execute MPI? So there's a command MPI exec. And as I mentioned before, I can run the same code on multiple number of machines. So I can specify the number of machines by using the -n, that is the n flag. I can write numprocs as say 5, 6, 7, depending on how many processes I want to spawn. And then I specify the py file, which is literally your Python code, which you want to run on multiple machines. Now that we know that MPI allows us to actually spawn this process on multiple nodes or multiple cores, what does MPI itself contain? So MPI has basically communication routines. For example, as you might imagine, two processes might need to communicate with each other. So there are protocols for receiving and sending messages between any two specific processes, or there are also interfaces so that one process can communicate with several processes, or like several processes can send message to a particular process simultaneously. Then there are also synchronization mechanisms specified in MPI. So you might want all processes to pause for a certain reason, all processes to end a particular session, something like that. So you have synchronization. As Sarthika already mentioned, the communicator creation and manipulation methods are also there. So as she already mentioned, there might be multiple communicators in a single MPI program, but for our discussions, we'll just keep it to one communicator. And then there are some advanced features like you can actually define user-defined data types, or you can also do parallel IO, but those are advanced concepts which we'll not touch upon in this presentation. So to move on, MPI in action. You can basically imagine, say P0 is our master node in which, say it's my computer, and then I have a bunch of 3 computers apart from my own computer, and I want to run MPI on all those 4. So what I'll do is I'll execute this command, MPI -n for Python, and then the hello world program. I can run it on my machine, and I'll also need to specify like if these are actually different machines, I need to specify the IP addresses of these machines. Or in case I do not have multiple machines, but I have 4 cores in my machine, I can just run this command on my computer. And what it does is basically, you can think of it as this hello world.py file actually goes on to each core or each node, and then it executes independently as if I individually went to each core and just did Python hello world.py. So now let's come to one of the first methods that we already said MPI supports, that is sending and receiving messages. We'll start with send. So it's a method which has the following signature. So as you can imagine, the send method would require at least 2 objects or 2 arguments, which is the object, like what do you want to send? And the second information you need is whom do you want to send it to? So the obj parameter would say that, okay, I want to send a NumPy array. Say process 2 wants to send a message or send an array, for example, to process 5. So it will specify something like this. So you can send O1, which is any form of data you can imagine. So node 2 can execute send O1 5, 1. Now, what is this 1? 1 is basically a tag. So I can additionally, so tag is an optional parameter. I can additionally specify, say if I want to send 5 different messages and I want them to be received by the process 5 in a particular order, I can specify that order in the tag. So I can say, for example, if I want to send another message, I would do send O2 5, 2. So that's how 5 would know that, okay, tag number 1 is a different message, tag number 2 is a different message. Of course, this is optional. I can actually skip the last parameter. So when 2 sends a message to 7, as we see, it does not specify a tag because there's no order required maybe. So that's basically tag is for identifying the message, but the broad signature is that what do I want to send and whom do I want to send? Where do I want to send? Now there are some things to note. For example, you can imagine that during execution of send, all further instructions would be blocked. So this is actually a blocking call. the return value of the send method gives you a status kind of thing in which you can know whether or not the send was successful. And then there's an additional caveat, meaning we don't need to worry about this, but it's just something that you have to consider. That is that the send method may actually complete. So the send call might complete even before the data reaching 5. That's because if the object is small enough to contain in a buffer, you will actually execute the send even before like receive the object being received at 5 or 7, for example. But we don't need to worry about this right now. Now the counterpart of the send is the receive method, which is the recv method in MPI, in MPI for Pi, and it again specifies those two things. That is, the first is buffer, which is like if I receive something, where do I keep it? So you keep it in the buffer. You also specify the source, meaning from where do I receive the message, and then the tag is the same as previous. And then additionally, there's a optional parameter called status, which gives you information like where did I receive the information from, what was its tag. So you can think of status as aggregating all the information which are the parameters like the source and the tag. And now you can also see that source has a default value of none, meaning it's perfectly fine if I do not specify a source. That's because if I do not specify a source, it would just receive a message from any process that has sent a message to the receiving process. So in this diagram, we can see that the process 2 or the node 2 executes a receive b1 comma 7. So it receives data from 7, similarly from 5 or from 1. So again, this is also a blocking call. So when the receive is being executed, all the further instructions on that node would get halted. And one more thing to note here is that if I do a receive call, but then no one had sent me any data, so it will just stop there. It will keep on waiting till it receives a message, because as you know, receive is a blocking call. So that call won't succeed and your program will pause. So you need to keep in mind that whenever you do a receive, you should be absolutely sure that there should be a send counterpart for that being executed somewhere else. Now, there are some helpful methods which almost every MPI program will contain, which is the get size and the get rank method, which Sarthika briefly mentioned. Get size is basically in my pool of processes or in my group of processes or the collection of nodes, the parameter that I specified during execution, that is the numprox, that it gives the size. So basically how many workers are there. And get rank basically enumerates each of those processes as a self-identifier kind of thing. So if there are five processes running in my MPI world. So it would basically have the processes would have values ranging from 0 to 4. So because there are a total of 5 processes. Now let's go on further to yeah. So now let's see our first MPI program. So in classical, you might have seen the classic Hello World program, but because this is MPI, we'll have the Hello Worlds program because we'll execute Hello World multiple times on different nodes. So we start off with the import of MPI for Pi, which is required for all these methods. Then, as I mentioned, the communicator, the rank, and the get size methods. So you can imagine if I execute this with 4 nodes in my world. So these 4 commands would be executed simultaneously for all of those. So the communicator will be shared among all those. The rank would be different for each of those nodes. And the num worlds, that would be the same for each, because that's the total number of processes in my pool. Now here is where it gets interesting, because now I can, based on my rank, I can do specialization, or you can call it as divergence. So I can specify that if my rank is not 0, that is my rank is 1, 2, or 3, I can send a message to the process 0 by like doing com.send data. In this case, data is basically hello world. So I'm sending a message from all the other processes to the process 0, which is just a text string hello world. Now, if my rank is 0, as I mentioned, like if I'm sending something, I should also receive something. So that's when I do in the else case, that is when the rank is 0, I can poll each of those processes and execute com.receive. And so starting from 1, 2, and 3, I will receive hello world, hello world, hello world. and like the output would be something like this. So in this case, like, yeah, because I had 5 processes, you can keep the number as much as you want. But so assume that we ran it for 5 processes. So you'll have process 1, 2, 3, 4, each one saying hello world. So this is not incredibly useful, but now let's move on to one of the examples wherein we do some actual computation, that is computing area. So what I mean by computing area is, imagine if you have a function and you want to find out the area under that particular curve. In mathematics, we can do this via integration, but if you want to just approximate it, you can do something like this. So you can divide the x-axis among multiple points, and then each of those points you can basically imagine a rectangle, and then you sum up the areas of all the rectangles in your x-axis, which will give you kind of an approximation of the area under this curve. So where does MPI come into picture now? So what you can do is basically, if you for example, in this case, I divided the total curve into 4 parts. What I can do is I can keep process 0 as kind of a synchronizer, and then, or even without synchronizing, basically each of those 4 areas can be computed by 4 different nodes. And then one of those 4 processes will basically aggregate all those areas and like output the result. So in this case, I assume there's a function called find area, which gives you which takes in 2 parameters. The first parameter is the interval, that is, how many intervals do I have? Sorry, what's the interval length of each of the intervals? So in our case, the size is 4 and the end is 8 because it ends at 8. So the interval size is basically 2. So to find the area, you need the start point, that is on the function, basically which rectangle to consider. And then you also need the width of the rectangle, which is the interval itself. So each of the process would have its own local area. By local area, I mean process 0 will have this rectangle, process 1 will have this rectangle, and so on. So at this point, each one has its own area computed with itself, and all of this has happened parallelly. But then I orchestrate the work using rank 0, meaning the process with rank 0 would basically aggregate all those areas, like it will receive areas, and then it sum it up in the variable total area. And then on its counter processes, that is like process 1, 2, and 3, would basically send those areas. So imagine it in the reverse order, that process 1, 2, 3 send their local area to rank 0. Rank 0 already has its own area, and then it receives the messages and adds the others areas into its own area. And then basically you can add a print statement here, meaning you'll print out the total areas. So rank 1 computed an area of 6, and then 8 and 10 and 12 for the other ranks. So this is how it would work. We have done with the basics now, that is sending and receiving, but there are some operations called as collective operations in MPI, which basically doing multiple things at the same time. So for example, broadcast is basically, if I want to send a message to every other node, I would do a bcast call, that is comworld.bcast. You can ignore the comworld thing, it's common for all the MPI methods. But broadcast basically sends a particular object from a particular node to every other node. So everyone would have to call this, but the data would be sent only from root is equal to 0, that is process 0. So this is just a schematic figure. It's not how actually it works. It won't go from 0 to 1, 0 to 2, 0 to 3. It has some internal optimizations, but you can imagine it conceptually to be like this. Then there's a reduce function, which basically takes an array of objects, or it takes a set of objects and then reduces that set to a smaller set using some operation, for example, sum. So imagine it to be like, if I do a reduce on an array with an operation called sum, it would basically sum up all the values in the array and give you one single result. We'll see one example where this can be useful, but you can imagine like reducing a set of objects to a smaller set of objects. Now, how do I use this reduce method in the area example that we saw? So if we go again, I mean, if I just do send and receive, I have to do like a for loop in the rank 0 to basically accumulate all the areas and keep on doing that. But then with reduce, my life gets easy, because now I can just do com.reduce local area. Now, what this does is basically till this point, everything is same. That is, everyone has found its own local area. But then when I do com.reduce local area, what this does is, by default, process, every process will execute this, of course, but then only the root result, only the root process would have the result. So by default, the root process is process number 0. So this total area variable would be populated only for root is equal to 0. That is the process 0. But then the default parameters for reduce is sum. So what it will do is sum up all the local areas for each of the processes and give that result only to rank is equal to 0. The process with rank is equal to 0. For others, total area would be undefined. So that's why I do, if rank is 0, I print out the total area because I know 0 has a sum of all the local areas for my all the other processes. And the MPI finalize is basically another directive which tells you that, okay, my program has executed and I want to stop my program. Now, this is fine. Like all these examples, you can kind of consider running on my machine with 4 cores or 8 cores and each core doing its work. But then how do we basically scale it to running on multiple machines? So in my MPI in action slide, I said like we can specify IP addresses. So this is how we do that. On each of the node, obviously, you should install MPI for Pi, the package. And then I also create a machine file wherein I specify in the network all the IP addresses of all the machines that I want to run MPI on. And then I do something like this. Additionally, I specify a machine file argument, which takes on this machine file. And basically, when you run MPI now, your network knows or your computer knows that, okay, these are all the computers in my network, which I should run MPI on. Now let's come to the one of the last points that we want to discuss, that is things to keep in mind. So as you know, MPI might sound complex, and additionally there are some more things which we should keep in mind. That is, the first thing is like not everything can be parallelized. Sometimes it's tempting to speed up even a process which is not inherently parallelizable. So you have to keep in mind that not everything can be sped up. Some programs are inherently sequential, and they should be inherently sequential though. Then we also should think about the paradigm. That is, when designing MPI codes or parallel codes, you should visualize how the data should be moving between different processes. That helps incredibly in designing such programs. A good practice to do is like first do a serial version of your program and then turn to parallelism rather than just directly jumping into parallel code. And then debugging is kind of messy, because you can imagine that you're not just debugging on one machine, you're debugging it on a group of machines. So you have to test your code multiple times. Again, to reiterate, we should not basically try to optimize early and try to optimize unnecessarily. You can only optimize so much, and it's not always possible to like optimize or speeden up every single part of your program. So you can keep some parts parallel and some part should be left sequential. The next point is optimize communication over computation. So you should take this away that communication is really expensive in MPI. So if there's a chance in which you have two options, that is, one, you can reduce the communication, and second, you can reduce computation. So always pick communication. Then another thing is it's perfectly fine to interleave communication and computation, because if you have some processes, if you have a process running like doing some computation and then doing a bunch of computation and then doing a bunch of communication, so it's actually better to do a bit of communication than compute, and like intertwine both of these processes one by one. Again, like to just quickly wrap this up, you can like pack as much data as possible in a single communication round rather than doing multiple communication rounds with like little bits of data. And like collective operations, as I mentioned, are optimal. That is, they have been written in such a way as to optimize the communication costs. So you should use them, for example, broadcast and reduce. And the last version is like there are multiple versions in MPI. So you should definitely do some research on choosing the right version. Now I'll hand it over to Sarthika for a quick trivia.
Yeah, so now let's get ready for a trivia. So how this will go, we will present you some statements and there will be binary answers for that, like either true or false. We will wait for, we will pause for 5 seconds for you to think on the answers and then we will reveal the answers. Yeah, so the first statement is number of processes should be same as the number of processors in MPI. Yeah, so this is false as it is not mandatory for the number of processors to be same as the number of processors. We can schedule more processors on the same processor, but it's a bit unoptimized to do so. Yeah, now let's go to the next one. Yeah, so next is MPI bcast is just a replacement of the send and receive loop. Is it true or false? Yeah, so this is false because it's not a replacement of the send and receive loop. It's an optimization on top of that, and it's used for sending to multiple nodes instead of a one-to-one communication. It's a one-to-many communication. Okay, now the next one is the main library for MPI in Python supports both Python 2 and 3. Yeah, so this is true. So MPI is like MPI has been quite some time in Python. It's so we have support for like it has support for both the Python 2 and 3. Yeah. Now this is MPI can handle communication between processes in Python using shared memory. Yeah. So true or false? Yeah, it's false. So it's not using shared memory. Like it's processes have they use the same they don't use the same space, but actually the memory is not shared between them. They have their own address spaces. So it's not they don't use shared memory. Next is the rank in MPI is the number of processes in an MPI communicator. Yeah, this is false. As you might remember that we discussed, size is the number of processes in the MBI communicator. Rank is used to identify the processes and not the number of processes. Now the last one is MPI can be used for network communication in Python. Yeah, this is false as MPI is not a network communication protocol. It's a message passing protocol. Like it's an interface for that. Yeah, so that's all from us. We hope that the session was helpful. We are now open for questions. Thank you.
Thank you.
Can errors made in a node be contained within that specific node? Or if a node unfortunately has an error because of hardware or software issues, will it be, I don't know, will it scale up to the root node itself, affecting the entire program?
Yeah, I can take this. So if it basically depends on how you have designed your Python code itself. But if you're, for example, the root node is waiting for some other node to send it some data and that node has failed. So the root node would just keep on waiting. But if like some part you have already gone past the part where it needs synchronization. So other nodes can just continue working. But then again, if you think about it, it won't be a super useful parallel program if there's no communication happening. So definitely, if one of the node breaks, most likely the complete workflow would break down.
I see. I guess that's why it's important to really test. A question
Yeah.
from Thank you. A question from Stephen is number one, can we define a machine file that lists only one machine multiple times? Does executing the same program on this machine perform the same or better than Python's multi-processing library?
Yeah, so I guess I'm not totally sure for the single the same machine IP address multiple times, but what I imagine would happen is that it would just perform as like it equivalently as I'm just running MPI on the same machine with multiple cores. It would just spawn on the other cores, but I'll have to get back on this. And regarding the second question, that is the multi-processing library. So both are very comparable. I would say some of the, as I said, collective operations, that is broadcast kind of operations, are better with MPI because they're super optimized. But then both of these libraries are like intended to do the same thing. So yeah, I mean it depends on the program, but I would say collective operations are faster in MPI.
Okay, maybe I'll call Sarthika this time. Like, what are the overheads in using MPI exec?
So, yeah, MPI exec, I'm not completely sure of, like what exactly that does, but yeah, yeah, I can take this up later, maybe.
Yeah,
Offline.
it's much better that
Yeah.
way. I would also like to ask, in distributing programming again, is it still relevant to be used in cloud servers, given that, for example, in Google Cloud, instead of just buying additional servers, you can just buy a bigger server and have more resources than it. When should I use distributed programming in the case of cloud programming?
Yeah, so the thing which you mentioned, like increasing the computing power, that is known as vertical scaling. And the one which you mentioned, like distributed one, in which we don't increase the capacity of a single machine, but we add more machines and have communication between them, that is horizontal scaling. So it ideally depends on the use case and the problem which you are trying to solve. So if the problem which you are trying to solve, it can be like distributed across different machines, and you can actually write code to combine those tasks and get the answer, then it's better to go to horizontal scaling rather than increasing the computing power of a single machine. But if you think that the problem at hand can't be actually optimized by using parallel programming and it cannot be distributed on different machines, and actually it will make it more unoptimized if you do so, then it's better to go via vertical scaling and increase the computing power of a single machine. Yeah.
Okay, thank you. Since, of course, parallel computing is not a one-size-fits-all solution, which brings us to the question of Carl, like, what are the use cases where you think parallel and distributed programming should not be used?
I
Yeah.
have an example on which I had worked like regarding this like I was just like to jump in. So during my undergrad, so we were working on this all pair shortest paths solution. So you have a graph, you have to find out shortest paths between every pair of nodes. So in cases where the graph itself is smaller, then it does make sense to use distributed computing. But if you imagine the graph is super dense, you can just imagine the amount of data that you'll have to send between nodes, and the communication cost is so much that basically even if you have 8 machines, you're still slowing down your program. So it depends on the graph topology. So if you have a very simple graph and you know that the edges, like there are not many paths between any two edges, then it shows a really nice speed up. But as and when the graph gets more and more complicated, you're just slowing down your program so much that it's actually better to run it sequentially. So yeah, that was one example which I wanted to just share with you.
I see. How about you, Miss Sartika?
Yeah. So I think the horizontal and vertical scaling which I covered, it depends on the problem at hand, and Vikram like rightly put it forward via this graphs example. So yeah, I think you have to basically understand this problem and how you have designed your solution, and then it eventually makes sense to further optimize your design and think about these two cases, like when to use parallel versus like should we parallelize or should we not. That all depends on the design of the solution. Yeah.
I see. So you always have to ask yourself the question as to whether you should parallelize or not. And I'm also
Yeah.
sensing that if communication between nodes are too much, then you
Yeah.
should not use
Yeah, you
parallel
should
computing.
avoid that. Yeah, because it will be an overhead. Like it more resources will go in communication rather than actually doing the computation.
Ah, I see. Another question from Stephen is, are there non-blocking send or receive calls? If so, what are the use cases for using them?
I think it's blocking only as far as, yeah, so because it needs to be synchronized, otherwise they can mess up the communication between different nodes. So I'm I am aware of synchronized only. Vikram, if you know, is there some non-blocking one? Yeah.
As far as I know, they are blocking. I don't know if there are other methods other than send and receive, but as far as I know, they have to be blocking because otherwise the communication cannot go on further.
I see. So the common use case is basically it's blockings and receive calls. Okay. I'm actually excited to try start one after this whole talk. I'd like to try on parallel computing, but I would like to ask for every beginner out there, what are the advice that you would give to them? And what are the common mistakes that you oftentimes encounter when creating parallel programs?
Yeah. So yeah, so as we have been discussing along, for beginners, first you should be comfortable with the basics of Python and how it actually works. There was this mention of global interpreter lock, right? And processes, threads, and async IO, and all these terms, which we skipped on because our focus was on MPI. But first, get comfortable with these terminologies and how they actually work. Once you get a hand on concurrency, parallelism, and the basics, then it makes sense to move to these advanced libraries and try out things. Uh, in that also, start with the basics, the Hello World program which we mentioned. Start with the very basic, try it out, just see how it is working, put logs in it, and then uh, try to analyze that what you thought is actually happening there in the code. After you get a grasp on that, then we can you can move to the advanced ones. So these I think that this is how I follow when I try to learn any new technology or something. Start with the very basic and try with the very basics. You can clear your concepts. With advanced ones, you should you will directly start coding and all. So concepts should get cleared at the very beginning for you to move to the advanced level. And I can Vikram can take the second question. Yeah. Second was, I think, this. What was the second question?
The second question is the same as Ben's question. What are the usual mishaps while doing distributed or parallel programming?
Yeah, that's a good question. So I mean, network is always not reliable, so you cannot rely that every time that your program would succeed. If there are issues in your network, then obviously it would not succeed. Then latency is always not zero. It depends on, because it's such a random thing. Like if one of the CPUs suddenly starts performing some there's rogue activity going on in that, it will just slow down in the entirety of your program. And then again, like bandwidth is not infinity. You have limitation in your bandwidth, depends on the communication channels itself. And then, but MPI itself is sophisticated enough that, mishaps like memory management would not happen. So that is obviously taken care of. Some other process cannot corrupt the memory of some other node. So that is all taken care of. But all these variables, this is where mishaps usually occur.
I see. That's why probably a lot of planning is needed when creating parallel applications. Speaking of parallel applications, I believe they're not typically known in Python, or at least based on my experience. Because if you're talking about parallel computing, it's always C, C++,
Yes.
probably some Java. I'm not so sure. Why do you think is Python not commonly known as a language that can be used for parallel and distributed programming?
Yeah, as far as I am aware, so the earliest implementations of MPI, like these bindings, were done in C++. So they gained a lot of popularity, and already because C++ is really fast. So I mean, there's obviously some inclination there, but then as and when these bindings, so for example, Java, the MPI bindings for Java, it's still not completely done. I mean, there have been developments there, but you cannot find like a very good resource on learning MPI bindings in Java. So I think it's just the game of like who got these first, and then because Python is incredibly popular and it's incredibly easy to learn for a beginner, so I imagine its popularity being grown would grow in the coming years. But yeah, I mean that's how I think about it.
Yeah, and like Python is used in so many like data processing, data analytics, and all these data related stuff. Then you like adding parallelism on top of it, I also think is a beneficial thing. Yeah, because yeah, the spread of Python makes us use it in Python. Yeah.
Yes, Python is literally everywhere nowadays.
Yeah.
Yeah.
Another question from Stephen. This is really good, I think. Assuming that there are several Python scripts using MPI for Py running in a node, how can you guarantee that the data sent is received by the right node and the right script?
So I think we can specify the receiver node in the function which we are using. The send function, it has a parameter to specify the node which will receive the data. So that is how you can specify.
So it is inbuilt in the MPI for Py, right?
Yeah. So the
Yeah.
function it is the this thing. The function has that parameter.
Yeah, so every time you want to send or receive, you have to specify from whom do I want to receive, from whom to whom do I send the message. If you do not specify it, then there's a possibility. I believe there was a slide in which you do not specify who I am receiving the message from, then it would just take any message that it gets. But for sending, you at least need to specify to whom do I send it.
I see. I guess it's up to the developer to really specify to whom they send it to ensure that it gets sent properly. From
Oh yeah,
NIMS,
I mean,
yeah, go on, Vic.
yeah, yeah. So I mean, it's really up to the coder of the program to determine how exactly the communication would happen. So it's up to the programmer. So you can even if the program is parallelizable, you can do a really bad job of communicating, but you can, I mean, there's scope for always improving the way in which you communicate. So I can do like some haphazard communication between 1, 2, 3, 4, 5, but then there's always an intelligent way to do that. So it depends on how you design your program.
I see. At the end of the day, it still depends on the developer whether they want to
Yeah.
shoot themselves in the foot or not.
Yeah.
Okay. From NINS, the question they ask is any specific algorithms you prefer when doing distributed programming? For example, using a bit tonic sorter for distributing sort and the likes.
I also citing like one of my recent experiences was say if we have like this was one of the projects which I worked on. It was not in Python, but it's still the same principle. So if I wanted to figure out if I want to read a large text file and then do some data processing on it, you can basically do text. Basically, if you have some textual task, so you can read the data and then chunk out your text processing, the text file into multiple chunks, and then each of the node can do like independent processing because usually your textual tasks would not be related to each other. So if you want to find out the intent, so you could just divide up the paragraphs. Each paragraph or each article would have its own intent. So everything can go in parallel without any like cross dependency. So yeah, typically the tasks in which you can figure out that there are multiple tasks and they are kind of independent. That's a good way to use parallel programming.